Today I am going to read a chapter from Pradeep's Organic Chemistry book of Semester 4 by Dr. S.N. Dhawan. The chapter is Chapter 10 Diazonium Salts. 10.1 Introduction. Arene diazonium salts were discovered by John Peter Gries in 1858. They are the general formula Ar N2 positive X negative, where Ar stands for aryl group and X may be any anion such as Cl negative, Br negative, NO3 negative, HSO4 negative, BF4 negative, etc. Aliphatic diazonium salts are also known, but they are highly unstable. They rapidly decompose even at low temperatures, forming carbocation and nitrogen gas. Rn positive triple bond NX negative is equal to R positive plus N2 plus X negative. Therefore, in this unit, we shall discuss the chemistry and synthetic applications of arene diazonium salts only, particularly with reference to benzene diazonium chloride. 10.2 Nomenclature. Diazonium salts are named by adding the suffix diazonium to the names of the aromatic compound, following by the name of anion. For example, benzene diazonium chloride, para-toluene diazonium hydrogen sulfate, para-nitrobenzene diazonium fluorborate, para-chlorobenzene diazonium bromide. 10.3 Structure of benzene diazonium chloride. First, molecular formula. The molecular formula of diazonium chloride as determined from analytical data and molecular weight determination is C6H5N2Cl. Second, Gries structure. Gries proposed structure 1 for benzene diazonium chloride, in which both the nitrogen atoms were directly linked to the benzene nucleons. This structure, however, failed to account for the following facts. First, its salt-like character. Second, displacement of both the nitrogen atoms by a univalent atom or group in most of its reactions. C6H5N2Cl is equal to C6H5X, whereas X is equal to H, OH, OR, Cl, Br, I, Cn, etc. 3. Its reduction to phenyl hydrazine, in which only one nitrogen is attached to the benzene ring. C6H5N2Cl in presence of SnCl2 or Na2SO3 gives C6H5NHNH2, that is phenyl hydrazine. Fourth, formation of azo compounds by coupling reaction. Fifth, formation of aromatic diazonium salts from penta-substituted anilines. Third, Kekule structure. Kekule proposed structure second for benzene diazonium chloride, in which only one nitrogen was linked to the benzene nucleus. Evidence in favor. Structure 2 explains most of the drawbacks of Gries structure 1, such as its reduction to phenyl hydrazine, formation of azo compounds by coupling reactions, preparation of diazonium salts from penta-substituted anilines, and displacement of both the nitrogen atoms by a univalent atom or groups. Point against Kekule structure. Structure second cannot explain first, its salt-like structure, second, its instability as compared to azo compounds, since both contain N double bond and linkage. Fourth, Bloom strand structure. Bloom strand suggests structure 3 for the benzene diazonium chloride, in which the nitrogen attached to the benzene ring is pentavalent while the other is trivalent. Evidence in support. It explains all the objections of structures 1 and 2. Structure 3 is further supported by the following facts. First, its reduced solubility in water but not in common organic solvents. Second, its complete ionization as shown by conductivity measurements. Third, the presence of a triple bond as shown by infrared spectroscopy. Fourth, its instability as compared to azo compounds. Fifth, it explains the geometrical isomerism as shown by diazotates or diazoates, which are the metallic salts of diazonium hydroxide. The sodium benzene diazotate can exist as a pair of symmetrical isomers due to hindered rotation about N double bond N bond. 10.4 Preparation of diazonium salts. Aromatic diazonium salts are generally prepared by adding a cold aqueous solution of sodium nitrite to the solution or suspension of a primary aromatic amine in an acid at 273 to 278 Kelvin. Diazonium salts are also formed when aromatic primary amines react with nitrite esters such as amyl nitrite. The nitrite esters needed for the purpose are prepared by treatment of alcohols with nitrous acid. Thus, this process of conversion of a primary aromatic amine into its diazonium called diazotization. General procedure for diazotization. The primary aromatic amine is dissolved or suspended in a dilute acid such as HCl, H2SO4, etc. 3 moles of an acid are generally used for every mole of the amine to be diazotized. 1 mole to form the salt of the amine, 1 mole to liberate nitrous acid from sodium nitrite, and 1 mole to keep the reaction mixture acidic enough to suppress the undesirable sides reactions such as coupling of the diazonium salt thus formed with the free amine. The amine solution is cooled and a cold solution of sodium nitrite is added slowly to it such as the rate that the temperature of the reaction mixture does not rise above 278 Kelvin. The addition of a sodium nitrite solution is stopped as soon as new few drops of the reaction mixture produces a blue with starch potassium iodide paper showing the presence of unreacted nitrous acid in the mixture reaction. Too much excess of nitrous acid is generally avoided since it subsequently interferes with the reaction of diazonium salts. Too excess of nitrous acid may be destroyed by the addition of urea. Since diazonium salts slowly decompose even at low temperatures, they are used immediately after preparation. Mechanism. The diazotization of amines is believed to occur by the following mechanism. Evidence in support. The mechanism is supported by the observation that aromatic amines containing electron withdrawing groups such as NO2 are less easy to diazotize. This is due to the reason that the nucleophilicity of the amino group is reduced due to the electron withdrawing effect of the NO2 group, as shown below. Such amines can, however, be diazotized in acetic acid. Conversely, aromatic amines containing electron-donating groups at ortho and para positions undergo diazotization much more readily than aniline. 10.5. Stability of diazonium salts. Aromatic diazonium salts are much more stable than aliphatic diazonium salts due to the dispersal of the positive charge over the benzene ring as shown below. Alternatively, the instability of diazonium salts is due to their tendency to eliminate an exceptionally stable molecule of nitrogen to form carbocations. Since the phenyl or aryl carbocations is much less stable than alkyl carbocations, therefore aromatic diazonium salts have much lower tendency to eliminate nitrogen than aliphatic diazonium salts. In other words, aromatic diazonium salts are much more stable than aliphatic diazonium salts. 10.6. Physical properties. Arene diazonium salts are generally colorless crystalline solids highly soluble in water. Many diazonium salts, especially nitrites, are dangerously explosive in dry state. Therefore, they are never isolated but are usually prepared in situ and used immediately after their preparation. However, certain diazonium salts such as fluoroborates are relatively insoluble in water and are stable enough to be dried and stored. Some diazonium salts also form complexes with metallic salts such as zinc chloride. These complexes are generally insoluble. 10.7. Chemical properties. Arene diazonium salts are highly reactive compounds. Their reactivity arises due to excellent leaving ability of the diazo group as nitrogen gas N2. They are therefore extremely useful synthetic reagents in organic chemistry. The reactions of diazonium salts are broadly divided into two categories. A. Reactions in which the diazonium group is replaced by monovalent atoms or groups. B. Reaction in which the nitrogen atoms are retained. A. Reactions in which diazo group is replaced by monovalent atoms or groups. Some important reactions of this category along with their synthetic applications are discussed below. First, replacement by hydrogen deamination. The replacement of the diazo group by hydrogen or the reduction of diazonium salts to arenes is usually brought by treating a diazonium salt with hypophosphorus H3PO2 acid at room temperature, preferably in presence of copper first salt as a catalyst. This reaction can also be carried out by treating amines with sodium nitrite and hypophosphorus acid as diazotizing agent. Alternatively, diazo groups may be replaced by hydrogen by heating arene diazonium salts with ethanol. For example, arene diazonium salt plus CH3CH2OH in presence of heat gives arene plus N2 plus HX plus CH3CHO. This whole process involving the diazotization of an amine followed by reduction of the diazonium salt or replacement of the diazo group by hydrogen is called deamination. It may be emphasized here that during the reaction of diazonium salts with ethanol, two products are usually obtained, viz. One involving the replacement of the diazo group by hydrogen as discussed above and the other by the ethoxy group. The relative amounts of the two products, however, depends upon the nature of the diazo compound and the alcohol used. If AI group is present in the nucleus, the ethanol is used. The replacement of diazo group by the hydrogen predominates. If on the other hand methanol is used, the predominant product is aryl methyl ether, that is anisole. Mechanism. The reaction occurs by a free radical mechanism as illustrated below. Propagation. Synthetic applications. The importance of deamination is illustrated by the following applications. A. First, synthesis of M-bromotoluene. Recall, M-bromotoluene cannot be prepared by direct bromination of toluene or Friedel-Crafts alkylations or on bromobenzene due to ortho-para-directing nature of the methyl group and the bromine atom. Second, synthesis of 1,3,5-tribromobenzene or symmetrical tribromobenzene. Third, synthesis of 3,5-dibromotoluene. Recall, direct bromination of toluene with Br2FeBr3 gives 2,4-dibromotoluene. 2. Replacement of hydroxyl group. Synthesis of phenols. Diazonium salts react with water in presence of acids to form phenols. The reaction is generally carried out by adding the solution of a diazonium salt to a large volume to boiling dilute sulfuric acid. The acidic conditions minimize the side reactions involving the coupling of phenol with diazonium salts. Mechanism. This reaction occurs by SN1 mechanism as given below. Synthetic applications. This reaction is especially important since only a few methods are available for the direct introduction of the hydroxyl group into the benzene nucleus. Synthesis of M-nitrophenol. Third, replacement by halogens. Different methods are used depending upon the type of halogen to be introduced. First, replacement by the chlorine or bromine, that is Sandmeyer reaction. Aryl chlorides and bromides can be easily prepared by treating a freshly prepared cold aqueous solution of an arene diazonium salt with a solution of cuprous chloride in hypochloric acid or cuprous bromide in hydrobromide acid. This reaction is called Sandmeyer reaction, which gives aryl halides in 60 to 80% yield. It may be noted here that in the halogen which is attached to copper which enters in the nucleus, mechanism of Sandmeyer reaction is believed to occur by a free radical pathway as delineated below. Gattermann reaction. It is a modification of the Sandmeyer reaction in which copper powder and a hydrogen halide are used instead of cuprous halide dissolved in the corresponding hydrogen halide. Yields are often lower, around 40%, than those obtained by Sandmeyer reaction. Synthetic applications. First, synthesis of 1,2,3-tribromobenzene. B. Replacement by iodine. The replacement of the diazo group by iodine does not require cuprous halide or copper as catalyst. It is simply achieved by treating a diazonium salt with potassium iodide or a solution of iodine in potassium iodide. Synthesis of para-iodonitrobenzene. C. Replacement by fluorine, that is Balch-Schimann reaction. When an aqueous solution of a diazonium salt is treated with fluoroboric acid HbF4, diazonium fluoroborate gets precipitated. It is filtered and dried. Unlike other diazonium salts, diazonium fluoroborates are fairly stable compounds. When dry diazonium fluoroborate is heated, it decomposes to produce aryl fluoride and boron trifluoride. Synthetic application, that is synthesis of fluorobenzene. Fourth, replacement by the cyano group. Synthesis of nitriles. Aryl nitriles can be prepared by treating the diazonium salt with cuprous cyanide and potassium cyanide and copper powder. To avoid the loss of cyanide as HCN, the diazonium salt solution is the first neutralized with sodium carbonate and then treated with cuprous cyanide. This reaction is called modified Sandmeyer reaction. Synthetic application. Since hydrolysis of nitriles gives carboxylic acid, therefore synthesis of nitriles provide us with an excellent method for the preparation of carboxylic acid from nitro compounds. For example, 5. Replacement by the nitro group. Nitro compounds are generally prepared by treating an arene diazonium fluoroborate with an aqueous solution of sodium nitrate in presence of copper powder. 6. Replacement by an arsenic acid group, that is BART reaction. Treatment of an arene diazonium salt with sodium arsenate in presence of copper sulfate followed by acidification gives an aryl arsenic acid. 7. Replacement by an aryl group, that is Gomberg-Bachmann reaction. When an arene diazonium salt is treated with the aromatic compound liquid or its solution in an inert solvent if solid in presence of an aqueous alkali, biaryls are formed. Yield is usually less than 40%. Mechanism. The reaction is believed to occur by free radical mechanism. In alkaline medium, diazonium salts are converted into the corresponding azo compounds which decompose to produce aryl radicals. B. Reactions in which nitrogen is retained. First, reduction to aryl hydrogens. Arene diazonium salts upon reduction gives good yields of aryl hydrogens. This reduction can be brought about by a number of reagents such as stannous chloride, hydrochloric acid, sodium sulfite, sodium hydrosulfite, and even electrolytically. If, however, strong reducing agent such as ZnHCl is used, the product is a aromatic amine. Mechanism of reduction of diazonium salts with sodium sulfite. The reaction probably occurs through nucleophilic attack by the sulfur atom of the sulfite ion on both the nitrogen atoms, forming the dianion of hydrogen sulfonic acid, which is then converted into hydrogen in presence of acid. Second, coupling reaction. Arene diazonium salt reacts with highly reactive, that is electron-rich aromatic compounds such as phenols and amines to form brightly colored azo compounds. This reaction is known as coupling reaction and is extensively used in azo dye industry, whereas coupling with phenols occur in basic medium, that is pH 9 to 10. That of amines occur in faintly acidic medium, pH is 4 to 5 at 273 to 278 Kelvin. Coupling usually occurs at para position with respect to OH or the NH2 group. If, however, the para position is blocked, it occurs at the ortho position. For example, benzene diazonium chloride plus p-cresol in presence of OH, pH is equal to 9 to 10 gives 2-phenyl azo 4-methyl phenol. If a compound contains both an amino group as well as hydroxyl group at para position with respect to each other, then the orientation of the coupling reaction can be changed by changing the pH of the medium. For example, that is given below. The well-known indicator methyl orange, which is widely used in acid-base titrations, is obtained by coupling the diazonium salts of sulfonylic acid with N and dimethylaniline. Mechanism of coupling reaction. The coupling reaction between benzene diazonium chloride and phenols or amines is an example of electrophilic substitution reaction in which the diazonium ion acts as a electrophile while phenol or amine acts as a nucleophile. A. Coupling with phenols. Since benzene diazonium ions are only weakly electrophile, therefore strong nucleophiles are needed for the reaction to occur. Further, since phenols is a weakly nucleophilic but phenoxide ion is strongly nucleophilic, therefore coupling reactions of phenols are usually carried out in alkaline medium. Role of pH. The pH of the medium plays an important role in the coupling of phenols. As stated above, coupling of phenols is carried out in the weakly basic medium as explained above. In the alkaline medium, the diazonium salts first forms diazonium hydroxide which immediately rearranges to diazo hydroxides which further reacts with alkali to form the corresponding salt called the azotate. All these three species in fact exist in equilibrium as given below. Since at high concentrations of OH negative ions, the equilibrium will shift in favor of diazohydroxide and diazotate, both of which do not couple. Therefore, for the desired coupling reaction to occur, the pH must be kept as low as possible in the alkaline medium. However, a too low pH would suppress the dissociation of phenol to phenoxide ion. Therefore, to carry out the coupling reaction, an optimum pH is needed. In actual practice, the optimum pH for the coupling reaction is between 9 to 10. B. Coupling with amines. First, tertiary amines. The mechanism of coupling reaction of diazonium salts with tertiary amines is similar to that of phenols except that the coupling is carried out under weakly acidic conditions. C. Reactions with primary and secondary amines. Coupling of diazonium salts with primary or secondary amines occur in a neutral or mildly alkaline medium. Here, NH2 group of the first amine first attacks the diazonium cation to form diazoamine benzene. However, when the diazoaminobenzene thus formed is heated in the presence of acidic medium, it undergoes diazoaminoazo rearrangement to form para-aminoazobenzene by the following mechanism. Role of pH. In the presence of high concentrations of H positive, the lone pair of the electrons of N accepts the proton. As a result, the amine exists predominantly in the protonated form as shown below. Aniline is equal to anilinium ion. Due to the presence of lone pair of the electrons of the N atom, the amine is no longer nucleophilic and hence the coupling reaction will not occur at the high concentrations of H positive ions, that is low pH. Further, as explained above, too highly alkaline high pH will also not favor coupling reaction by forming unreactive diazohydroxide or diazotate salt in significant amounts. Therefore, an optimum pH of 4 to 5 is employed for such coupling reactions. Thank you.